Okay, guys. Guys, we'll continue now. We'll continue. Ahmed? We're continuing now. Now, what we're going to have a look at, something called hypothesis testing. You might even know this word just from basic science. Test a hypothesis. I don't know, is this vocabulary you've had in your labs? Biology and chemistry?
Never heard.
Yeah? So what hypothesis did you test in biology? Yeah, but what's the hypothesis? As a sentence, what were you testing?
We were actually testing the pH and the optimal pH and the optimum temperature of an enzyme.
Yeah, so that's not quite then hypothesis testing because you're trying to estimate something.
Yeah, because we're not given the...
Yeah, so what about in chemistry? Any hypothesis you tested in chemistry?
It was actually, the neutralization is supposed to be exothermic.
Good, okay, so that's a hypothesis. In other words, a hypothesis is some claim was made and you need to test the claim, usually with some kind of experiment. Okay. The reason we're looking at binomial, or rather the meaning of the word binomial here, is because we're looking at things which can either be, happen or not happen, true or false, yes or no. We're just looking at sort of data that can take two values. This is a little bit different to perhaps what you did in the lab because you were measuring things, whereas this one we're just counting how often something happens or not. I'll give you a simple example. So one example here is we flip a coin, heads and tails, and we flip it a total of 10 times. And in total, or let's say our data looks like this. So you get heads, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 like that. Okay? Got your pen? Oh, okay, so who am I adding now for the next class? Who did I just get? Mubarak and Shadera. Okay. Right. Mubarak, don't just come in talking. Come on. Right. As I was saying, we flip a coin 10 times and we get the following data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 heads. Now there's something a bit unbelievable about this, right? If somebody said to you that this coin is fair, would you think this data supports that hypothesis or not? No. It's very difficult to support the hypothesis that the coin is fair if you've just flipped it 10 times and got 10 heads. However, it is possible that it is fair and this just happened by chance. So we need some way of measuring how believable a hypothesis is. So suppose instead of flipping the coin 10 times, I flip it 3 times. And my data is now, it's still all heads. It's a bit more believable that it could still be a fair coin, right? So there's something quite different about these two that makes this one a bit more believable than the first one. So before we advance any calculations, we just need a little bit of vocabulary. So we have two things which we call the null hypothesis, null, and then the alternative hypothesis. The null hypothesis and the alternative hypothesis. So these are like what you might say your claim and the counterclaim. So for this example here, the claim, you're claiming that the coin is fair, that this is a fair coin. And what would be the alternative to that? What would be the counterclaim? Unfair coin. Now it's good to put a precise number on what you're saying. So when we say the coin is fair, what we're saying is the probability of a heads should be 0.5. And when we're saying the coin is unfair, what we're saying is the probability of heads is not 0.5. Okay. This is called a two-tail test. Now it's not called two-tail because there's two hypotheses here, because there's always two. The reason we call it two is if we have this situation, you're testing an equal against a not equal. That's the reason we call it a two-tail. I'll give you an example of other types now. Can I scroll down? Yeah? We're not doing any calculations just yet. I just want to make sure we got the vocabulary. So let's say we have this data. Again, we'll say 1, 2, 3, 4, 5, 6, and then 1 tails then here. Now, it's not really, to be clear, we kind of know that the coin is not fair. So we're not quite testing whether it's fair or not fair, but to be a bit more precise, what we're testing is this. The null hypothesis is that it's fair, fine, that's p is 0.5, but the alternative to being fair, to be more precise, not that it's unfair, but rather the probability is actually more than 0.5, because it would be too unbelievable to accept that the coin is unfair and in fact it's biased towards tails. That's too inconceivable of a possibility even worth stating. You know, if I said here's a coin, it gave us heads 1, 2, 3, 4, 5, 6 times, tails once, and it's biased towards tails, tails shows up 90% of the time. That's too outrageous of a hypothesis even to actually consider. So really we're only considering that the coin is fair or it's biased towards heads. And we're not even going to consider the possibility that it's biased towards tails in this situation. This is called a one-tail test. And the reason for one tail is you're testing equals against half the alternative. So it's either equal or more than. And we're not considering the possibility that p could be less than 0.5. We've thrown that possibility away in our considerations. Okay, so this is an example of a one-tail test. Okay, can I scroll down? Yeah? Yeah? Okay, so if you're wondering, does it matter if you swap these two around? So for example, if you say something like, you know, in the first example we said the null hypothesis is that the coin is fair and the alternative is that it's unfair. Is it possible that you could say it the other way around? That the coin is unfair and then the alternative is that it's fair. And we don't really say it this way around. And the reason is we kind of imagine that we assume everything is normal. We assume innocence and then we try to prove guilt. So we assume the coin is fair, and the alternative is that it's unfair. We assume like the innocent explanation, that everything is normal and usual. And the alternative, the guilty explanation, is what we try to prove. Okay? So it actually does matter which way around you say it. The null is kind of like what you might call the innocent explanation, whereas the alternative is what you might call the guilty explanation. So try to get them the right way around, okay? You might want to make a little bit of a note of that. So you could just, whatever words you want to say, the null hypothesis is the innocent, natural, not an unusual explanation, and the alternative is the sort of guilty, unusual, something strange is happening explanation. Can I scroll down a little bit? So like, before we do a calculation, just one more example. So let's say we have a class, 50 male students, 50 female students, and the teacher is selecting a group of, let's say, 6 students, and the teacher selects male, 3, 1, 2, 3, 4, 5, 6. So 4 males and 2 females. And we want to know if the selection is fair, or perhaps the teacher is favouring one gender over the other. So what would we state the null hypothesis here, and what would be the alternative?
The model would be that she's fair.
Yeah, that the teacher is selecting fairly. So it's a fair selection. That the P is 0.5. And the alternative would be unfair. Yeah. Okay, so we're getting, and is it this one or 2 tail? 2. The way we have it stated here, it's 2. I could change it to 1 tail if I do this. Replace this word unfair with bias towards male. Now it's 1 tail. Yeah. Yeah. It's okay? Get which part? Yeah, so this one here, so in the first case, we've considered the possibility that it's fair versus it's unfair, that there's some bias towards one of the genders, but I didn't say which gender. In this case, it's fair versus the alternative explanation that there's bias towards male. I now am no longer considering that the teacher is biased towards female students.
And would you specify that, or would
Now,
specify that?
the exam sometimes asks you to state the hypothesis. So you have to now they say in the question both the null and the alternative. They'll say in the question what the story is and what you need to test. So for example, this question could be something like, a student wants to know if the selection process is a fair process or if the teacher is showing favoritism towards male students. Then I would write it like this. If it said, the student would like to know if the selection process is fair or the teacher is biased, then it was like the original one. So they'd be really careful with the words, you know.
They sound the same to me.
I know, but can you see any difference?
No. If you have,
None.
If you have favoritism, doesn't just mean that you're biased.
Yeah, but if I said the teacher is fair versus have favoritism, that's different to the teacher is fair versus they have favoritism towards boys. In the first case, I'm not saying which way the teacher is showing favoritism. If you look at it, it's kind of obvious, but I'm not specifying that. In the second case, I am. It's a small difference.
So when you say that the teacher is unfair, is that a two-tailed?
Yeah, it is, yeah. Yeah. Because you're still considering the possibility that the teacher could be biased towards favouring female students. It's unlikely to be true here, though. Okay, so now, how to test whether or not the hypothesis is true or false, because that's the whole point here. This is very important for research and for medicine. I'll give you an example. Can I scroll down a bit? So we'll do our first proper example. So let's say you have 20 people taking part in some study, and you give them some treatment that helps them recover from the cold faster. So, no, 20 is a little bit too big. Let's make it a bit smaller to begin with. Let's just say 10 people in the study. And here's our data. So it's binomial because there's two situations that can happen. Either the person recovers from the cold within a week or longer than a week. Okay, so if I write W, that means they got better within 1 week of getting the cold. And then if I write W dash, it means it took them longer than a week to get better. Okay, so let's say we have week, longer than a week, longer. So what's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 here. So let's just add that up. How many patients got better in a week? 1, 2, 3, 4, 5, 6. And it only took more than a week. Do I not have 10 here? It's 4 then. Okay. So obviously the drug is trying to help people get better in a week. So looking at this, would you say that this drug has helped people get better in a week or not? No, you can't. Not necessarily. Because you don't know. Maybe most of the time people get better in a week anyways. So we need to know what we're testing against here. So perhaps in normal life we'll say 40% of people get better naturally in a week. So 40% get better in a week. Now that I've said that, do you think this data is supporting the hypothesis that the drug is helpful or not? Well, not entirely convincing, is it? Like if I have 10 people, how many do I expect to get better in a week naturally? 4. Because I said 40% get better in a week. And in this trial, how many people did get better in a week? 6. So, okay, maybe the drug has helped, or maybe we just got lucky and 2 people got better in a week by chance. Okay? So, before I tell you, I want to give you a minute to state the hypothesis and the alternative hypothesis. Now you need to imagine that you're the person doing the research. This will help you write down what you're actually claiming and what your counterclaim is. And this drug is supposed to help you get better sooner. So it's a study, 10 people, and it's a study of new cold meds. Okay, this is a little bit tricky, but I wonder if anyone got a null hypothesis for me. So, any ideas? Yeah? What do you think? And then I can see yours next then. Yeah? No?
6 were
No. No, I'll stop you there. No. It needs to be a little bit more punchier than that. Mahmoud? That's too short. We need somewhere in between. You're giving me not enough detail and you're giving me too much detail. Not enough details. You need to have some numbers in it. Nearly, yeah. Yes, nearly. Not quite, not quite. So what the null hypothesis... Now, you're halfway there, but the number you got wrong is the 60. Because 40% of the time. No, 40%. Because remember we said, what's the null hypothesis? It's the innocent hypothesis. So the innocent natural explanation here is that the drug isn't really doing anything and people are just getting better at a rate of 40% of the time. So the natural null hypothesis here is that the rate that people recover in a week is still 40%. And the alternative is that it's more than 40%. You would love if this is true because it means your drug is curing people at a rate more than the naturally occurring rate of 40%. Can you see that? Now, the difficulty in this lesson is really with the vocabulary and picturing what exactly you're saying. Yeah?
Yeah, I've got a question about null hypothesis.
Yeah.
I'm not sure if I'm mistaken or not.
Yeah.
I couldn't find the page where this is on, but I remember null hypothesis being something like when nothing happens or when there is no difference.
Well, that's what I'm saying when I say innocent. So, you know what I mean when I say innocent? Like that the drug isn't really doing anything. So if the drug's not really doing anything, how many people should get better? 40%. Yeah? Is this no, we need to be clear on this. If there's questions, please ask. We'll do more examples as well. We'll continue. I know it's confusing. I know it's confusing because when you go on to do research for medicine, you're going to be using language like this. And I know a lot of people have confusion with that because I give a lot of people private lessons at university when it comes time to submit their masters and they're like, I don't know what I'm doing. Okay? So I'm just, I'm trying to help you save money now so you don't have to pay for a tutor in the future. Okay? Also, this is on the exam. Right. So how do we calculate? So this is how we calculate whether or not we should believe the null or the alternative. What we do is we calculate something called the p-value. And let me say what the p-value is. This is the probability of the data, or more extreme, given the null hypothesis. So I'll explain what that means. The probability of the data or more extreme given the null hypothesis. That means what is the chance of getting this data or a more extreme result if the null hypothesis is true? Can I scroll down? And I'll show you how to calculate this. Yeah? Okay, so what you do, we start backwards here. Given the null hypothesis. So imagine that it is true that P is actually 0.4. We want to calculate what's the probability of getting, weak and not weak. What was it, S 6 and 4? 6 and 4. That's the probability of the data, or more extreme. And by more extreme, we mean a result that would be more favourable to believe in the alternative. So if I got 6 people better in a week and 4 people not better, what would be a more extreme result? That would be even more supportive.
0.6.
What number changes could I make here? 7 and 3. That would be even more extreme than what we got, wouldn't it? Or, what would be the next one? 8 and 2. 9 and 1. And the last one? Now, if you got 10 people got better in a week, and 0 people didn't, so 10 people got better in a week, that would really, which would that support? The null or the alternative? The alternative, wouldn't it? Like, it'd be really strong for it, okay? So a way we can calculate which one is likely to be true is we calculate all these probabilities and add them up. Now, these are all binomial, so what's the first one? It's 10C6 0.4 power 6, and the next one is
0.6 power
4. And then we continue with the other ones, okay? I'll give you a minute to calculate that.
I remember reading something about p-values and p-hacking and how it doesn't slow it.
Let's not complicate our lives. I think most of the class would agree our life is complicated enough. And it's only 10:18. So. Now, if you're all using your calculator, you're all a bunch of suckers, because you've completely forgotten that you have a table book that can do this for you. Oh, yeah. So, what were you just doing there? You were doing 6 or more W's, which is the same as 1 minus not 6 or more. So what's the opposite of 6 or more? 5 or less, is it? Yeah, 5 or fewer W's. Okay? So here, what's the n? The n is 10. Yeah, the x is 5, and the p is, what's the w? 0.4. So it's 1 minus that book value.
Isn't this 4?
What's 4?
4 or fewer? 6 or more.
Oh, sorry, thank you, apologies. You're right, sorry, you said it as well. 4, yeah, not... this was a 6, yeah, sorry, 4. That's the opposite of 6 or more, isn't it? No, now you're confusing me. It is, I was right the first time, 5 or less, yeah. If I have 10 people, and... No, it's... can people see that?
No.
No? I'm sorry, man. Everyone else can see it. Right? Guys?
I think it's just the one I've done.
If you have 10 people, 6 or more means 6, 7, 8, 9, or 10. What's not having 6, 7, 8, 9, or 10? That's 5, 4, 3, 2, 1, 0. Processing. I can see the Apple Mac icon turning. Are you giving me the final answer? 0.1662. Okay. Can I explain now? Continue? This is the answer after you did 1 minus. Yeah, okay. So it was like 0.84 in the book or something, was it? Yeah. Now, this is the last part of the hypothesis test. Now, guys, listen. You can work together in a second. Just give you the last piece here. The last part of the hypothesis test is the decision. So, do you decide that you have evidence for the null hypothesis or that you have evidence for the alternative? So, the rule is this. If this p-value is less than 5%, you reject the null hypothesis. And if the p-value is more than 5%, you do not reject it. So, yeah, but we'll get to that in a second. Which situation do we have here? Greater than. So do we reject this claim? If somebody made the claim that it's actually 0.4, do we reject it or not? We do not reject it. So what does that tell us about the efficacy of the medicine? Do we think this medicine is effective or not? Guys, you got it exactly opposite. Not effective. Because we've just said, do you reject the claim that the medicine cures at a rate of 0.4? No. So the medicine, we think, cures at the rate of 0.4. What's the normal rate? It's 0.4. So the medicine is literally doing nothing to change this. Yeah. No. Less talking, more thinking. I'll say it again. Listen carefully. Listen carefully. I'll say it again. Listen. So, we have 16%. So that means we're in this situation. We do not reject the null hypothesis. So this claim that the rate that the medicine works at is 40%, we do not reject it. In other words, we accept it. We think it could be true, that the medicine works for 40% of the time. But we just said at the beginning that 40% of people will get better in a week anyways. So what good is this medicine? No good. So we've answered the question about the efficacy here. The medicine is not doing any better than naturally occurring rate. And you see, the language is quite difficult here. We will, of course, practice another one now. This is our first example. Okay? So, you'll have to write this down. Now, by the way, this 5% number, this is just considered a standard. We call it a 5% test. It's considered just the standard percentage to use. It's used in medicine as the standard number here, 5%. There's no rule that says it has to be 5%. We just need to pick a number where we can make a decision between the two. It's possible that we're wrong. It's possible that the medicine does help a little bit, like maybe 41 or 42%. We weren't able to decide that. So it's possible. The only way that we could know for certain is if we do the experiment again with maybe more people. Yeah. Okay, so if you write this down, we'll do another example. Now, I'm going to let you ask me only one more question for the rest of the class, so decide if this is the question you want to use. No, are you going to keep that question reserved for later, or do you want to use it up now? Reserve, good call. Okay, write this down, we'll do another example. Can I scroll down to another example? So by the way, guys, listen. If you were doing this in a paper that you were writing, you would just say in the paper, we do not reject the claim that the medicine works 40% of the time. And then you would put in brackets, p-value equals 16.62%. So when you're reading a paper and you see numbers like p-value equals 2%, p-value equals 6%, it's coming from this test. Okay? So I mean, I don't know if you've read papers for your biology essays or anything like that. Have you done your biology essay?
Yes.
And did you have to read papers for it?
Yes.
And did you come across any papers that use this vocabulary?
Yes.
P-values? Yeah. But glossed over it? Yeah, okay. Yeah. Right. Here's another example. So let's say we have some application for university, or maybe some department, this I don't know, whatever it is, department A, I'll just say. And in this department, we'll say that 60% are female and then 40% are male. And then each year, perhaps there's a group of people that are selected, maybe for some kind of scholarship of some sort. So we'll say that 20 people are picked for a scholarship. And let's say 16 of them are female and 4 of them are male. And the person is selecting these 20 people. So at the very beginning, it looks like, is there a possibility that the person is selecting in favor of women here? Well, it looks like it from here. There's 16 females to 4 males. However, this person is selecting from a group where there are 60% more females than males. So it's not entirely clear from these numbers if we could say there was some kind of bias going on here. So suppose the question we'd like to know is, I'll call this person, I'll just call them S, not S for Stephen, S for selector. So that S is bias, no, just that S is, we'll make it clear that S is a sexist pig. There we go, okay. Right, so what I want you to do for me is, what I want you to do for me first is state the null hypothesis and the alternative hypothesis. That's his question. No, the question as in the claim, the question we want to answer. Yeah. It's really, really, really good practice to have some number mentioned in the null hypothesis, yeah. You can't just say null hypothesis, S is not a sexist pig. Like we have to put some quantifiable number in it.
Is that 16? Oh, to the right.
60, 40, 16, yeah, I'll fix that. 16 and 4. 16 and 4. Yeah, I think you have it, John Pang, so just keep that to yourself. Let's see if someone else can. Does anyone else feel like they have it?
Yeah.
What do you think it is? That's an awful long pause for someone who knows it.
I know, but I don't want to say it.
Okay, fine. That's fine. Anyone else? Depends which way around you state it. So, I would say the null hypothesis is the innocent hypothesis. And what would be the innocent here? That they're not sexist. So in other words, the probability that they select female, so just to be clear, I'll just write P with a little f here. That should be 0.6, not 0.5. Why is that? 60%. Right? Like, take an extreme example. Imagine that there were 90% of the population were female, and you selected half your group to be female. That doesn't make you a equal opportunity selector. So you're only not sexist if the rate that you pick females at is the same as the rate at which they appear in the group. Yeah? Okay. Now, think carefully though about what the... Now you have to really look at my choice of language here. What's the alternative here?
Greater than 0.6.
Bigger than 0.6.
No. No.
Greater than 0.6.
No.
Greater than 0.4 for male.
So that makes the alternative and the null the same, which is... Yeah?
Greater than 0.4 for male.
No.
Less than 0.
No.
Now you continue.
0.25.
Where the heck did you get that number from? Not 0.6. Now, let me explain why.
My favorite is male.
Well, yeah, I never specified in the question which way the person was sexist, did I? I just said that they were sexist. I didn't say they were sexist in favour of. I know this is difficult, but that's why we're doing this now, so you try and get your head around it. So is this one or two tail? Two tail, good. Two tail. So, let's try and calculate the p-value. So remember what the p-value is. It's the probability of getting the data, or Mubarak Daniel, please, I'm trying to talk here. Remember what the p-value is. The p-value is the probability of getting the data or more extreme. So let's just do the first one, the probability of getting the data. So p is 0.6 and what's the data here? 16 females and 4 males. Or, what would be more extreme? What would give us more evidence that they're sexist? The alternative. 17, 3. 18, 2. 19, 1. And then, oh, 16, 17, 18, 19, this is 20, 0 then.
15. You could go both ways.
Yeah, well, that's the thing. Now, we have to go the other way, but not quite 15.5. So, the other end is the flip opposite for 16. If 4 women were admitted and 16 men, or 4 women were and... Wait, why am I writing 16? I don't really need to. 4 women were admitted. Would that indicate sexist result?
Yes.
Yeah, it would. And if it was 3 women, and 2, and 1, and 0, what's that? 3, 17, 18, 19, and 20. Now look, what will happen in real life, when you add up all of these, this one here, I think the total will be like nearly 0. Because these are so inconceivable as a situation. You know, if I said to you, the person picked 16 females, how likely is it that they'll pick, you know, like it's so different to what you got, it's quite small, I think. But because it's two-tailed, we have to consider both ways around. Now, I think we can do both of these quite easily using the table book, so it won't take you long to calculate. So I recommend that you do it as 2 separate problems, and then add the 2 answers together. Okay? So this is basically one tail, and this is the other tail. This is like the mirror image of extreme possibilities. Yeah? Okay. You're using it up. Go on.
So why is it that you cannot go with like 556? Do you know?
If you go 15.5,
Yeah.
the reason for that, is because the p-value is the extreme results. If you move into 15.5, think about it like this. We'll just keep it easy with a coin flip, okay? So I flip a coin 10 times, and let's say I get 8 heads, okay? And if the coin is fair, how many heads should I get? 5, if I flip it 10 times, right? And I got 8 heads. Which is more extreme? That I get 9 heads or that I get 7 heads? Which is taking us further away from the hypothesis being true? 9. If I move backwards, I go from 8 heads to 7. I'm actually moving to being in a more likely favourable position. So this is why I never go past my data into the favourable. I always look at the extreme, the unfavourable. So what would be more unfavourable here to the claim? 17 females, 18 females, 19 females, 20. But because it's two-tail, I have a mirror image. I have to look at the other extreme. So I swap the both numbers. Yeah. Let's see. Let's calculate. Right. So, let's do the one on the left. So this is the probability of, what's that, 16 or more. 16 females or more. But of course, our table book can't deal with more, so we have to do with less. So that's the probability of 4 males or less. Now, what's that? N is 20, isn't it? X is 4 and P is 4 males. We're counting males, so 4. Yeah, females were 6 then. Right, what number did that work out as? No, just the left one.
Yeah, 0.949.
0.949?
No. 1 minus 0.0510.
Okay, just
0.0510.
you go ahead. Yours sounded reasonable. What was it?
0.0510.
0.0510.
Yeah.
Okay. Right. Now this one here, what is this one? This is the probability of 4 or less females. What's the problem with this one in the table book? What's the problem with this? Well, the probability is 0.6. Can we look up 0.6? No. So instead of saying 4 or less females, we should say 16 or more males. But what's the problem with this? Can we look up or more in the table book? No. So this is 1 minus not 16 or more. So what's not 16 or more? That's 15 or less males. So that's 1 minus, and then N is 20, X is 15, P is 0.4. So what's the final answer for this side?
0.00003.
So remember at the start I said this should be effectively 0 because it's so outrageous. What did you get? 0.00003. But that's not surprising because I said at the beginning it's outrageous to try and consider the situation that the person is biased completely opposite to what the data might suggest. So, or means add. So what's the final answer? P-value equals 0.0513. Now you realize if you were doing this in the exam, you could have actually stopped here. Why? It's already more than 5%. So if you add something onto it, it's only going to make it even more. So this is equal to 5.13%. So what is the result if we are more than 5%? We do not reject. Yeah, we do not reject the null hypothesis. So, don't just blurt it out. Take a few seconds to think about it. Are we saying we have evidence that S is sexist or not sexist? Now don't blur it out, just take 5 seconds to think about it. Okay, now that you've taught at least 5 seconds. What are we saying here? Not sexist. We do not reject the null hypothesis, meaning that we think this could be true, and if this is true, that's supporting the idea that they're selecting in the right proportion. Now, it's not exactly convincing, is it? Because we're only slightly above 15%. I kind of think if the data was only slightly different, if it was 17 females and 3 males, I would suspect if we recalculated this, we might get something like 3%. And then that would be the alternative, wouldn't it? So it's just about believable that they're not sexist. Just about. But it's not exactly convincing. But the rule is, if it's more than 5%, then we don't reject it. And if it's less than 5%, then we do reject it. Okay. So as you can imagine, these are on the exams, and it can be quite difficult because there's lots of new, difficult ideas here. I can see some of you are starting to get your head around it. You really, really would want to try all of these. Like, you really have to make sure this knowledge is solidified in your head. Okay? Now, the first few questions are just practicing writing down the null and the alternative. You don't actually start calculating until question 6. Guys, I'll just finish with one question. I want to look at the book. It's a difficult one, but I just want you to think about it and see which way around you can get the answer. I just want to have a look at number 4. It's kind of a silly situation, but it gives us a good example. Can you all see number 4 there? Yeah. Right. Let's look at this one together. James Bond is given a sample of drinks which have either been shaken or stirred. So can you see how that's similar to all our situations? You either male or female, 1 week or not 1 week. And we, as the researcher, would like to know if he can predict whether, from just tasting it, it's been shaken or stirred. Is this a one-tail or a two-tail test? Now, I can give you, to help focus your mind, I can give you some data as an example, okay? So just imagine that the person half the time shakes and half the time stirs, okay? And let's say he says the data is, he gets the first one right, wrong, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's 10. Right, so what are we thinking here? Is this one tail or two tail? What do we think? Or if I prefer, I can make it even clearer for you. So let's say he says shaken, not shaken, not shaken, shaken, not shaken. And then Mr. Bond comes along and he says shaken, not shaken, not shaken, not, and shaken. So he got this one right, wrong. Oh no, sorry. No. Right, wrong, and wrong. Wrong. Yeah, okay. Right. So what do we say? Is this one or two-tailed? What do you think? Well, what are we saying about him?
That we can figure it out or not. You think that the hypothesis is that we could figure it out?
So the researcher would like to know if he can tell the difference.
0.6. Yeah.
Okay, so we're all happy that sorry, what is it? Oh, I made it 6, didn't I? Okay, fine. P is 0.6. I think we're all happy with that. He can predict right 60% of the time. But what's the alternative?
P is not 0.6.
Yeah, now we have the two choices. We can either say he's not right 60% of the time, or maybe it's he's right more than 60% of the time. Like if he was right 100% of the time, that would mean he can predict everything perfectly. So I want everyone to read what I said in the question and then decide, are we saying this or am I saying this? Now read the question and then tell me. We as the researcher would like to know if Mr. Bond can tell the difference between shaken or stirred. Is this one or two-tailed? In other words, are we saying this is the alternative or this is the alternative? Not or greater than. So the key word is tells the difference. So which should I pick here? First or second? First. Good. Because I said tell the difference. Now look at what I changed in the language in the second part. If instead we would like to know if he can predict whether it was shaken or stirred. That's the other one. Because what we'd like to know is if he's right more than 60% of the time. It's not easy. One last situation here. Here's the data. Here's the drinks. And let's say Mr. Bond said this. He said the first one, shaken, he said not. Second one he said yes, he's wrong again. This one here, wrong again, wrong again, wrong again. Now, does this support the claim that he can tell the difference between the drinks or not? Now, just think, is this in favour of him supporting the claim that he can tell a difference or not?
And the support of?
He can tell a difference or not?
He can tell the difference?
Tell the difference, yes.
Yes. Because he's gotten everything exactly the opposite. So he obviously can tell the difference, he's just not able to tell which is which, but he knows the difference. Now if I said to you, does this support the claim that he can predict whether it's shaken or stirred? No, because he's gotten everything wrong. Now you see, the English is very, very subtle here. The English is very, very subtle. That's why it's important that you should practice all of these. Because you know by tomorrow, if you don't practice, you will have forgotten everything. You will go to sleep and the files will be deleted from your mind. You know that, okay? So you really need to practice this. No, you don't hope so. No, you don't hope so. Because you've got a test in, the summer on this. Okay, so really, you really should practice all of these. We'll finish there.
So the second question, is it one tail?
The second one is one tail. And the first one was two tails. Can you see the similarities between when we did the examples of where we want to know if they're sexist or if we want to know if they're sexist towards men? It's like saying, this one is not as clear, I know, yeah. It's like saying we want to know if he can predict the difference or we want to know if he can predict correctly. So he's in favour of getting the right call, It's not, I know it's not easy. I know it's not. Yeah.